Hi, everyone, and welcome back. I hope you enjoyed those clips. We have three of the speakers on now here to answer your questions. We've had some amazing questions coming through. So I'm going to start with some of the questions. So there was a question from James about how do you estimate the number of asteroids at each size scale? And I think that question is best answered by Marco.
Yes, that's an interesting question. It's done in a not so easy and simple way. We basically, every night we discover new asteroids, and most of them at first are new because we have a lot of asteroids to discover. After a while, telescopes will start rediscovering the same asteroids. And the more we find, the more likely it will be to rediscover versus finding new ones. And by comparing these two numbers and how they evolve, we get a feeling of how closer we are getting to finding them all and how many we still have left. This is basically the way, this is actually modeled mathematically, but it gives us the information on how many are still missing and as a result, how many there are in each size class.
Thank you. So a sort of related question. So this impact probability, can you tell us how that's calculated?
Okay, yes, there's a lot of mathematics behind this, but basically, let's just make it simple. Let's just assume that we have some observations of an asteroid, and for these observations, are compatible with many different possible orbits. They're all going to be pretty similar, but they're going to be slightly different depending on how they fit with all the observations. So what we do basically is to compute all these possible orbits that are compatible with the observations we have, and then propagate them in the future, extrapolate them into the future, and count how many of them actually, when propagated forward, collide with the Earth versus the total. So the ratio between how many collide versus the total possible orbit that the asteroid can have are a way to measure the probability that the asteroid could actually collide with the Earth. Then obviously the mathematics is a bit more complex, but this is just a simple hand-waving description of how these probabilities are computed.
And again, how do you know how far the asteroids are away? How do you calculate their distance?
So yes, the distance is also a bit tricky. In most cases, we don't actually measure the distance of the asteroid. What we measure is basically we compute the size and the orientation of the orbit in the solar system from the observations. And obviously, when we can determine the size and how the orbit is placed into the solar system, by knowing where the Earth is, we can indirectly determine how far the asteroid is at any given time. In some rare cases, for very close and typically very large asteroids, it's also possible to directly measure the distance by using radar. By just bouncing a radio signal to it and receiving the signal back as a normal radar works. And this gives us a direct measurement of the distance of the asteroid at that particular time.
Fantastic. So you've talked about DART. When was that launched, and how effective will it be? How big an asteroid could it actually move?
Okay, it's not launched yet. It will be launched here, and it will hit the asteroid 2 years from now, in 2022. In terms of effectiveness, well, the technique itself is thought to be effective on asteroids ranging from a few hundred meters up to about 1 kilometer. It depends a little bit on how early you can do it. If you have a few decades to do it before the possible impact, then with a suitable large impactor, you can actually deflect it, even if it's about order of 1 kilometer. If you have less time, the same technique will be capable of deflecting a smaller asteroid. The main result that will come out of the DART and the AIDA mission is exactly that. It's exactly giving us the scaling law that we can use to estimate how big and how fast an impactor we need for each given size and orbit and warning time, so that whenever one comes, we can actually fine-tune our impactor properly to be able to deflect it effectively.
Thank you so much. I think actually that links in quite nicely to a question for Ramy, which is about this mass. Sorry, I've just lost the question now. There was a question about the the mass of different asteroids? And how do you know the mass of an asteroid? How do you predict what it's going to be from the material it's made of?
So that's a really interesting question. Excellent one, actually. So first of all, we have a pretty good idea of the average composition of the asteroids, simply because we've got so many pieces on Earth that we've analyzed tirelessly in our labs. We know exactly what's in these what's in these rocks. That's one thing. Second part is we can get more or less as well some approximate information of the composition of some asteroid using remote sensing techniques, such as spectroscopy, where we can, through the reflectance of light that's bouncing off these asteroids, we get some information about the mineralogy of the surface, and we assume that that's also linked to the bulk composition. So using that spectroscopy information plus all the information that we've got from all the rocks on Earth gives us a pretty good idea of the compositions. And once we know the composition, we have a pretty good idea as well of the density. So if you have a good estimate through imaging of a volume of your asteroid, then you can extrapolate, assuming certain range of densities, get a range of masses. So that's how you would do it in a remote sensing way. But if you actually do send a spacecraft, then just through the radio observations and using the instruments on board, you can actually measure how much your orbit, the orbit of the spacecraft, is gravitationally perturbed, and use that to very accurately estimate the mass of the asteroid. So if you are visiting it with a spacecraft, it's a very accurate measurement. Otherwise, we tend to measure the mass of the asteroids based on our idea of what they're made of and their densities. And once we have a good estimate of their size, we can estimate their mass.
Thank you. This actually might be a good chance to talk to Francisco, because I know, Francisco, you mentioned, sorry, Ramy, you just mentioned that the asteroids we have on, the meteorites we have on Earth. Well, I know Francisco actually has one on him right now, so he can show you that and talk a little bit about this particular asteroid.
Well, what I have here is a meteorite, which is about half a kilo, actually. It's an iron-nickel meteorite that fell in South America a few hundred years ago. And it is quite dense. I mean, it's the density of iron, which is about 8, I think, 8 times more dense than water. And these are very rare, in fact. I mean, they are easier to find because they have magnetic properties, and they're very different from any other rocks. But they are less than 10%, I understand, as abundant as the other meteorites are. The rocky meteorites are much more abundant than the iron meteorites. But it gives a very good idea of for dating. These are very good. You can date them very accurately. They have, apart from these metals, they have also strontium. They have ruby strontium isotopes. You can measure the ratio of this, which is a kind of, if I could here, a ticking clock, if you imagine that, of these atoms decaying slowly. And they have been decaying since the meteorite formed 4,500 million years ago, more or less. And they are ticking down, ticking down, ticking down. And we can measure the ratios at the moment. And this is how we can the age of these meteorites. It's fascinating. We can hold a piece of rock, a piece of metal, which is a little bit older than the solar system. That's amazing.
Thank you, Francisco. So we did have a question from Charlotte about what causes the unusual shape of the Ragu and Bennu asteroids, and why are they so similar? So, Ramy, answer that?
Yes, that's also an interesting question. So there's a distinctive difference between the asteroids in the asteroid belt and the ones that are very close to Earth, such as Ryugu and Bennu. So Ryugu and Bennu are what we call rubble piles. And these are asteroids that have been actually destroyed through collisions. They've disintegrated, particularly due to some of the gravitational influences, such as that I've mentioned from Jupiter. So they've actually sort of reaccreted and reformed new bodies again. And because of this, they actually have a lot of pore spaces in between. So you can think of them almost like a sponge. And in fact, asteroids like Bennu and Ryugu are thought to have maybe more than 50% pore spaces, empty vacuum spaces inside of them. So they've kind of were broken up and then they reaccreted, and they sort of reaccrete into a certain spherical shape. Now, because these shapes, these bodies also are very small, they have very low gravity, they tend to rotate, and if they rotate quite fast, then the tidal forces from that rotation tends to flatten them out a little bit and maybe create some tidal some tidal ridges in the equatorial part. And so the effect of the fast rotation that's occurring on these asteroids, and the fact that they have very low material strength because they're just rubble piles, materials that just accreted together after being completely disintegrated, give them this sort of kind of similar shape, because they have been in fact shaped by similar processes after being broken up.
Thank you. Another question for Marco, talking about the gravitational effects of other bodies. So as these things are traveling through the solar system, how are other bodies affecting them, and how can you account for that?
Yeah, another interesting question. In most cases, they don't affect them too much, but all the computations that we do take that into account. So the models that we use, for example, in ESA, we take into account the deflection, the gravitational attraction of all the planets, obviously, and of about 300 major asteroids in the solar system. It doesn't mean that they all actually do something. Most of these small asteroids don't actually affect the trajectory that much, but they're all modeled in the program, as are some other effects, for example, the relativistic effects, for example, the irregularities of the shape of the Earth. All of that is known because we know the masses, we know the shapes, we know the positions, and all of that can be taken into account by considering the effects, the gravitational attractions of all of these little effects, and using them to model the trajectory of the asteroid. So it's actually a pretty sophisticated model, mathematically and also computationally, as you can imagine.
Thank you. Another one for Ramy has come in about why is the asteroid belt where it is in the solar system?
Yeah, that's an interesting question. So the answer to this is we had actually bodies everywhere. There's nothing really special about the asteroid belt. You're simply looking at the particular location where small bodies never grew into a planet. So at some point, very early on, as the solar system formed, as I said, you had a lot of bodies that are accreting towards each other, creating very small planetesimals. And if allowed, these planetesimals grew into protoplanets and then planets. So all the small bodies that were in the sort of inner orbits got incorporated into Mercury, Venus, Earth, and Mars, or the larger chunks towards the outside got incorporated into the larger planets. And then due to Jupiter's influence, as I said, particularly for the asteroid belt, you end up with this area, the poor souls who just never had a chance to build a planet. So that's the main reason why the bodies would seem to be concentrated there. When we started off, we had small bodies everywhere in the solar system, but in favorable locations, these bodies grew into a planet, whereas in the asteroid belt, they never had that chance.
So there's a link question about that. Is how stable is the asteroid belt today? Is it a nice stable, or are there collisions and all sorts of things happening there right now?
So yeah, that's an interesting question as well. So dynamically speaking, the asteroid belt is being affected by collisions with bodies with each other. The influence of Jupiter is actually, with time, kicking a lot of materials out of the asteroid belt. So in fact, the asteroid belt has already lost a lot of material since it formed 4.6 billion years ago. Having said that, just as there are unstable orbits caused by resonance, you can also get stable areas. So just given them enough time, even if there are some stable areas in the asteroid belt, we might envision that at some point down the line, we may run out of bodies in the asteroid belt, simply due to migrating bodies, due to collisions where they just keep on fragmenting to smaller and smaller sizes. and the continued influence of Jupiter and other bodies that are acting on the asteroid belt. So in a sense, it's kind of dwindling with time, but slowly.
So quite a tricky question here, really. Francisco, I'm not sure if you can answer this or not, but so a new asteroid's being formed now, because you spoke about the asteroid you had in your hand being, you know, over 4 billion years old. Are there new ones being formed now? Do we know?
That's a very, very interesting question. I'm sure that other people are more qualified to answer that. But how do you make asteroids? They are coalescence of material which is loose in that protoplanetary disk, but also they can be formed by collisions, by fragmentation, when two big objects collide, and then you produce a shower of smaller objects. We could be talking about Saturn, for example, this stuff. But I wouldn't say that new asteroids being formed. You can asteroids that collide and they produce smaller fragments that become smaller asteroids. I would say something like that. I don't know if any of the other colleagues could add on what I just said.
I can echo what Francesco said as well. Basically, compositionally speaking, all the asteroids, all the small bodies formed 4.6 billion years ago when the solar system formed, and there's been nothing new being formed. But what is happening is that dynamically you can get new families of asteroids due to migration from the asteroid belt to the near-Earth asteroids, fragmentation of a larger asteroid into smaller families. So you might end up with sort of what we call dynamically new bodies. But as far as compositionally speaking, there are no new asteroids being formed in the solar system.
So that leads me on to another question, which is Marco, and you can join in afterwards. How, if we've got new ones being created and we're discovering new ones all the time, how are we naming them? Is there a convention about how we should name these things?
So why we still need to discover some, I guess. Well, the thing is, not all of them are easy to discover. There are some that have particularly peculiar orbits that keep them far from the Earth for long, long times, maybe for decades, and they only come close enough and they become observable only very rarely, maybe every 20, 30 years or something like that. So we haven't been doing this for a lot. The asteroid survey started basically 2 decades ago. So there could still be large asteroids that are still out there, been there for forever, but they are in orbits that keep them far enough from the Earth and hidden enough from our telescope that we haven't had a chance to find them yet. But with time, these orbits will move in a way that make them discoverable from Earth, so we will be finding them also. So it's just a question of time and the fact that we haven't been doing this activity for that long.
Thank you. Okay, so we have 2 more questions I'd like answered before we start on the next round of videos. The next round of clips is talking a lot more about the composition of asteroids. How do we know what they are, and how could we potentially utilize them? So some really 2 very interesting talks coming up. But talking about the composition of asteroids, does the composition have a big effect on how damaging an asteroid will be if it hits the Earth? I think that's probably a good question for Marco.
Yeah, it depends obviously on the size. I've given some examples in my talk. Basically, they go from nearly no damage at all, let's say in the few meters size range, to obviously major damage. That is like the absolute extreme would be the asteroid destroyed the dinosaurs and all these species that were alive at the time on Earth, a lot of species that were alive at that time. So I guess it depends mostly on the size. One could sort of estimate from size and velocity of encounter the kind of damage, but a lot of things depend on subtle details. For example, where it hits, the kind of rocky material, the substrate on the Earth, or maybe if it hits on the ocean. Some of it may also depend on the entry angle. Things that fall down vertically may have different way of dissipating the energy, and then things that come shallowly through the atmosphere. So it's a complex scenario. A lot of ingredients go into it. Some maybe than others to predict. For example, everything that has to do with the interaction of the asteroid with the atmosphere and the friction of the asteroid to the atmosphere and the thermal properties, that thermal phenomena that happen, that is tricky to model. But in general, the main dominant thing is the size and the mass. So that gives us a general idea. Let's say that anything that is kilometers is going to cause some very global event on Earth, very global catastrophe. Anything that is in the hundreds of meters may cause damage, let's say, regionally at like country level or continent level. Everything that is in the tens of meters is probably going to cause effects that are localized to a few tens of kilometers around the point of impact. And everything less than 10 meters is going to be minor damage or nothing at all, depending on what's under it. So just to give you a rough idea of the different size ranges and what they can do.
Thank you. So the last question, it sort of links into composition a little bit. Ramy, I don't know if you'd like to talk about a little bit about the Kuiper belt and these other objects that are further outside of our solar system.
So is that reference to the question on the size of the asteroid?
Size, but also,
Yeah. So that's actually a very interesting question. So asteroids, we would measure the shape and size simply by directly imaging them if they're close enough. In the case of the Kuiper belt, what we actually even did with the target of the New Horizons mission is we utilized an astronomical technique called stellar occultations. And what we do actually is we wait for that body to go in front of a star, and we are measuring the brightness coming out of that star before that body passes in front of it. And then as the body passes in front, we measure how much of the light, how less of a light we receive from that star. Because in a sense, that body, because it's coming between us and the star, sort of like eclipse part of it. So what happens is a decrease of the light coming from the star. And the amount of light that is decreased allows us to actually have a pretty good estimate, not just about the size of the body, but if we have more accurate measurements, even the shape. So that's generally speaking how we derive the size of very far away bodies.
Thank you very much. I'm sure everyone at home is been very thankful for the questions. Please do keep the questions coming in. We've got 2 more speakers coming up and then another Q&A session. So please go on to Slido, the Talking Asteroids event code, and you can get your own questions answered by our panelists. So thank you very much. Thank you, everybody.